start with the door opens first, and then we'll close later if that's fine with you, Doctor. Yeah? Okay. Excellent. Okay, ladies and gentlemen, let us now begin. I would like to first introduce our next speaker. Dr. Stefano Zanero received a PhD degree in computer engineering from the Politecnico of Milano Technical University, where he is currently spending his postdoctorate. His current research interests include the development of intrusion detection systems based on unsupervised learning algorithms, security of web applications, and computer virology. He is a member of the board of the Journal in Computer Virology and acts as a reviewer for the ACM Competing Reviews and IEEE Security and Privacy, as well as various primary international conferences. He is a member of the IEEE, the ACM, and a founding member of the Italian chapter of ISSA. He has also been a columnist for Computer World Italy and has been awarded a Journalism Award in 2003. Since 2004, he has been a partner and is CTO of Secure Network, a firm specializing in information security training and consulting based in Milan. Today, he will be presenting his presentation entitled 360 Degrees Anomaly-Based Intrusion Detection. Join me in welcoming Dr. Stefano Zanero.
Thank you. Well, actually, that was a very, very long introduction. I will shorten it to the fact that I'm Italian, so I don't speak a very good English, which makes up for an excuse for everything you will not understand in my talk. And please, if I'm talking badly and you don't understand me, or you don't understand something because you want to ask a question, just feel free to interrupt me at any point. There's no need to wait for the Q&A. If you want to wait, that's fine. But if there's something that you missed and you want me to re-explain something, please feel free to interrupt me during the talk. Basically, what I will do today is try to give you an overview of what we are doing at the Politecnico di Milano in the field of unsupervised learning and anomaly-based intrusion detection. Basically, intrusion detection is a way to try to answer to a very big problem, which is known in warfare as the defender's problem. Basically, the problem can be stated as simply as, while the defender has to defend everything, the attacker needs just to find one weak spot in a plan in order to succeed, which is very well known in all the areas of fighting, of sports, even in chess. There are no defensive chess players, because in order to win a chess game, you have to attack the opponent. Here, the problem is that you have to actually act sensibly. If you attend a 2-day conference such as this one, where a lot of good speakers give you insight on all the ways that you have to attack systems, you might be scared by the sheer number of vulnerabilities that haunt today's systems. And being scared is exactly the wrong approach to the problem. The right approach to the problem, as I think the actual status of the actions against terrorism underline nicely, the actual point in defending is acting sensibly, is not overreacting, is not acting driven by fear. So I advise you to buy a book which is Beyond Fear. It's written by Bruce Schneier. It's probably the first computer security book that any computer security practitioner should have on his shelf, in my opinion. Here I like to point out that there is a Murphy law which describes very well the status of computer security. The only difference between systems that can fail and systems that cannot possibly fail is that when systems that cannot possibly fail, they usually are impossible to repair and usually have devastating consequences because they are failing in a manner that you did not foresee. So the idea is that you have to plan for the worst. So you have to plan not for what happens if your systems are broken into, but for what happens when your systems will be broken into, because they will be broken into at some point in the future, and have probably already been broken into at some point in the past. I don't want to try to ask you how many of you have had a system which has been broken into, because then there will be two types of people in this, in this audience. The people who raise their hands and the people who are lying, either knowingly or unknowingly. Because every type of system at some point in the past or at some point in the future has been or will be compromised. So we must take lessons from what engineers have done for hundreds of years with machinery, with buildings. You have to build things that fail gracefully, where something is not essential and cannot be a total failure if something fails. You must build things that can be recovered. You must have backups and backups of the backups and so on. And you must build things that are tamper evident. Computer systems are not tamper evident. If someone breaks into your computer systems, there are good chances that you will never notice. So what is an intrusion detection system? An intrusion detection system is not the software package that you buy from your software vendor. An intrusion detection system is actually a system which is able to detect tampering with your computer systems. So if you buy a software package which performs intrusion detection analysis and you don't look at it, that system is not an intrusion detection system anymore. An intrusion detection system is software, hardware, and humans cooperating to detect intrusions. So a network administrator such as any of you looking at system logs is a better intrusion detection system than any instance of Snort left running, never updated, and never looked for. The question is, what type of intrusion detection systems do we need? There is a big taxonomy in intrusion detection between anomaly detectors and misuse detectors. If you have probably heard of this, but if you have never heard these two terms, it's because misuse detectors actually exist, and anomaly detectors actually do not exist, except in books, research projects, and a very, very limited number of products out there. There's a very good chance that even if you have an intrusion detection system in your company or in your organization, you have never even heard of the fact that there exist two different types of approaches to intrusion detection. Misuse detectors are the traditional kind of intrusion detection system that you may be used to. They are systems which have a knowledge base of attacks, of well-known attacks, and which look at different sources of data in order to try to catch those types of attacks, which is very, very similar in conception to what your favorite or non-favorite antivirus product does for viruses. The only problems are that, first of all, when a virus propagates, sooner or later, the guys from F-Secure, if you have heard Nico Iponen talking today, or from another company, will see that propagating and will create a signature for that. If someone creates a zero-day vulnerability, and since they are very, very evil, they don't even sell it on Wabi Sabi Labi. They don't even sell it on the IRC. They just keep it to themselves. So that's a true zero-day. Chances are that no one will ever write a signature for that vulnerability. So no misuse detector will ever be able to catch that exploit because there's no knowledge base to act upon. Unless for some chances, an old signature for another vulnerability casually catches also this vulnerability. But that's just a game of luck. The second problem of misuse detectors is the problem of polymorphism. Now, catch correctly what I mean when I talk about polymorphism, because I've been bashed, not rightfully, by David Maynor on this point on his blog. Polymorphism here is not intended as in the expression polymorph virus. A polymorph virus or a polymorphic shell code is just a virus or a shell code which randomly or semi-randomly mutates in order to try to avoid detection. When I'm talking of polymorphism of attacks, I'm talking of the fact that if you give the same vulnerability to exploit to all the people who are participating in the CTF out there, they will exploit it in different ways. Sometimes there will be a key point which is similar among these different ways. And you can catch that, create a signature on that. And you can catch all the different variants with just one signature. But on other attacks, there is no such key stepping point. And so you are left with the option of writing basically one signature for every known way of exploiting a vulnerability. Which means that if someone comes up with an ingenious new way to exploit the same old vulnerability, chances are your misuse detector, no matter how good the guys that are writing the rules are, will not be able to see that. On the other hand, anomaly detectors are the earliest idea of how an intrusion detection system should work. Intrusion detection was first described in 1980. In 1980, I was 1 year old, if this is of any use to you, to gauge how many years have passed since then. And when it was first described, it was introduced as anomaly detection, or the detection of anomalous activities over the networks or over the computers, actually, at that point in time. The idea is that if you're able to describe and to model the normal behavior of your computers, then at any time something anomalous happens, you can fire an alarm. And since attacks are usually intended to make your computers do something that they would rather not do in normal conditions, then attacks show up as anomalies, which is a great idea theoretically, but practically it's a couple of different limits. First limit is, how do you describe normality for a computer system? How do you measure it? Is the number of outgoing packets versus the number of incoming packets a constant which you can measure? Maybe so, maybe not. For some computer, it certainly is. The average number of emails a computer sends, a client sends on a network. If you're working in a company, those numbers are substantially stable, except during Christmas season, for instance, when people usually shoot unwelcome greetings and postcards and e-cards to everybody they know. So it's very difficult to find the variables that describe normality in a computer system. It's even more difficult to create models that can actually model those variables and catch variations and not generate tons of false alarms. Because this is the key difference between a misuse detector and an anomaly detector. The misuse detectors, the intrusion detection systems you work with commonly, do not have, read my lips, do not have false positives, or they rarely have false positives. Why is that? Because if a rule fires, chances are there's an attack ongoing. Even if you don't care about it, even if you didn't want to know about it, that's exactly a packet which matches with the rule. Maybe you activated a rule that you didn't want to activate, and that's your fault. But the tool itself does not generate or rarely generates false positives. On the other hand, an anomaly detector, by its nature, generates false positives. It's impossible to do anomaly detection without false positives. What you can do is to try to keep the false positives low and the detection rate high, but you cannot do no false positives. Which means that, combined with the fact that when you see a snort rule firing, you know that that specific attack has been performed. When you see an anomaly detector fire, you just know that something is wrong. But what is wrong is your guess. So basically, you cannot use anomaly detectors, really, for automated reaction, while you can use misuse detectors for automatic reaction, if you are so inclined. That's what's been marketed as intrusion prevention systems. So, in the universities, we work a lot on anomaly detection, basically because misuse detection is simple. It's difficult to engineer it and to create a product. It's not like ISS or Real Secure. It's not like ISS builds Real Secure and that's easy. It's a difficult product to build. But scientifically, it's not challenging to create rules and to create products that apply rules. Scientifically, it's challenging to create systems that do not need rules. And in particular, my research has been in the area of unsupervised learning. What is a learning algorithm? It's nothing fancy, it's nothing like Star Trek. A learning algorithm is an algorithm which gets better over time at doing whatever it's supposed to be doing. Because it learns, it stores information extracted from the data. In some cases, what you're using are supervised training algorithms. How many of you do use a spam filter? Any type of spam filters? I don't believe it. Raise your hand. Who uses a spam filter? So the other people do not use email, right? Your favorite client-based spam filter, by Easy and spam filter, whatever, usually has a button with which you flag spams that it did not catch, and with which you flag things that it incorrectly classified as spam. That's called a supervised learning algorithm. You give an example to it, and it learns from the example. You pre-classify things for it. You correct it over time. That's a supervised learning thing. Unsupervised learning is even more mysterious. It means that the algorithm sorts out things by itself. You don't give it examples. You just obtain results. It's not magic, it's mathematics, actually. There are two particular classes of unsupervised learning algorithms that I'm sure you will be as interested as me, no, probably not, in knowing. Outlier detectors and clustering algorithms. Let's see them briefly. Clustering algorithms are algorithms that can put together things that are similar and separate things that are not similar according to a set of features. This is a very, very nice definition, but it has two weak points. First weak point is, what do you mean by similar? Which implies defining a distance. And the second weak point is, according to a set of features, a set of observations. So what are the sets of features? Because, for instance, if I observe the current climate in Milan and the current climate in Kuala Lumpur, in Milan, there may be 35 degrees, as there are in Kuala Lumpur currently. It's not like that, actually. It's much colder in Milan. But the two climates are not defined by this single variable. So if I look just at the temperature and I said, okay, I will dress in Kuala Lumpur exactly like I would dress in Milan, I will be making a very, very horrible mistake. First of all, because in Milan, during the night, temperature changes. in Kuala Lumpur during the night is almost as warm as during the day. Because it's different climate, because you have to take into account different variables, different features. If you're trying to cluster objects, to cluster things, and you take into account the wrong features, you will end up with a wrong clustering. First thing. Second thing, even when you have features, in particular, if the features are not described by numbers, calculators badly suck at dealing with features. So if you have something which is green, and something which is blue, and something which is red, what is more similar between these three objects? As a human, you will probably say, well, it's three different colors, right? A computer cannot tell it that way. Or, for instance, if you have different colors and you want to group them by shades of color, you have to find a way, which can be your regular RGB way of describing colors, in order to let the computer calculate the difference between colors, which is something that we humans give for granted, exactly as we humans take for granted that I can see this thing over there, which is slightly obliquous, the other which is not obliquous, and call them, those are two chairs. And if I see outside a totally different one, I will say that's still a chair, because it has some common features with the other chairs of the world. It's very natural for me as a human to think like that. But to teach a computer how to call a chair is not easy. It's a whole field of research in the field of artificial intelligence. Yeah, I don't have the time to go through all the details. But the problem, basically summarizing it, is there is a number of algorithms that are useful to make a computer distinguish among things. And if you look at the literature on intrusion detection, all those algorithms, sooner or later, have been applied to intrusion detection with varying results. What we did was actually take someone, who was me, with some knowledge about how computer security in the field works, and taking some other person, which is still me, who actually studied how the mathematics behind these algorithms work, and put those two things together. And the outcome was quite satisfying, or at least it was worth a PhD degree, if that's any measure for you. I'll get to the actual algorithms and to the method in a moment. I just wanted to introduce the second big part of the things that we use, which is outlier detection. What does outlier detection mean? What's an outlier? An outlier is something which is so different from the other things that you have observed that you think that either it's an error or it's been generated by something totally different. Basically, the idea comes from industrial sensors. If you have a sensor which is measuring the temperature at some point in an industrial plant, and it says 100, 100, 100, 1,500, 100, 100, that 1,500 probably is a glitch. It's an outlier. It's something that you either want to explain in some context or you want to discard because it's evidently wrong. So, what's an outlier, for instance, in network traffic? The whole point of my work was trying to understand if this hypothesis holds. If we look at packets, at network packets, as observations, are attacks outliers? Because if they are outliers, I can detect them in some ways. If they are not outliers, if they statistically blend in with the rest of the traffic, then all the literature on intrusion detection done by using network traffic in an anomaly detection sense is rubbish. Well, turns out that it's not rubbish, luckily for me. What turns out is that if you look at the packets as what is called a multivariate time series, so a multivariate time series is a series of values, of sets of values that you measure. A time series is, I measure temperature here in Kuala Lumpur over a day, once every 10 minutes. I have a time series of temperatures. A multivariate time series is, I measure temperature and humidity here in Kuala Lumpur once every 10 minutes. It's a bivariate time series. Detecting outliers on univariate time series is simpler, of course, than detecting them over multivariate time series. The problem is that we have excellent algorithms for detecting outliers on multivariate time series that are made of real numbers, where real is used in the mathematics sense. But if our values are made up of those non-numbers that I was talking about earlier, yellow, green, red, or if you prefer, TCP versus IP versus ICMP, or if you prefer, TCP packet bound to port 80, 81, 8080, these are not real numbers. They are not even integer numbers. They are numbers that qualify a port. Okay? So it's not true that port 20 and 21 are closer than port 21 and 22. Not necessarily. So the whole idea is to find an outlier detection algorithm that works also on categorical data. And the impressive thing is that after extensive research on literature, I found out that basically there was no algorithm that could fulfill my expectations, but one which was almost what I needed. It's called Smart Sifter. It's been developed in Japan by Mitsubishi researchers. So it's been promptly released in some part and patented in some other parts. Being a university and not wanting to work with someone else's patented technology, which I couldn't afford, what I did was to rework the algorithm in a way that still makes sense mathematically, which is more suitable to my problem, and which is not covered by the original patent. So the Smart Sifter Z algorithm is basically a very, very similar thing to what you find described in the Smart Sifter papers, plus some modifications that you find if you look at my scientific papers. There's all the gory mathematical details that I cannot really discuss here. Then there's another very, very hard problem we are looking at here. A network packet usually, as you know, carries an unstructured payload, which is structured if you look at it decoding the particular transport and application layer protocol you are using. But if you look just at the bytes, it's something unstructured. The problem is that even my fixed Smart Sifter algorithm wants numbers or classes, but doesn't want things that are varying in dimension and that are of different structure. So you have two solutions. The solution that was used before my research was to discard the packet content. You just look at the headers, because the headers are convertible to numbers, and you can apply your favorite learning algorithm to those with minimal effort. Of course, this yields some results, in particular for instance, detection of denial of service attacks, port scans, this type of things. But in many attacks, the interesting data is in the payload. So if you don't look at the payload, you will never see these attacks. what I did was I used another learning algorithm, an algorithm that can perform clustering. So what I did was I picked up the payloads, I clustered the payloads, I used the classification of the payloads as an input to the supervised learning algorithm for time series. And what I had was a two-stage process that meaningfully picks up packets, transforms the packets into a real time series, and looks at the time series looking for problems. So what happens is, and this is the idea, so what happens is that there are a number of results that show that, for instance, you can recognize protocols through neural algorithms. So if you give some packets from mixed protocols to a clustering algorithm, the algorithm can separate the different protocols without you teaching it the protocols, without you giving it examples, because they are structurally different. Of course, this is not perfect. Some protocols are similar, and those protocols will end up in the same cluster. But what happens is that, for instance, if you look at two very different protocols, HTTP requests and FTP commands, they are classified in totally different and totally separated classes. So what about the attacks? Let's pick up, once again, the HTTP protocol. And let's try a number of attacks against the HTTP protocol, against not the HTTP protocol itself, but for instance, against various HTTP daemons, against various web applications. Let's look at the attacks that can be carried over HTTP. So attacks are orange. Normal traffic is orange. Attacks are blue. As you can see, the same unsupervised algorithm, which has separated HTTP traffic from other types of traffic, separates in a similar way most of the attacks in this particular and lucky example of the HTTP, all the attacks in other protocols, of course, which I won't show you because they are less impressive. It works not so well. But in most protocols, many attacks can be separated just by looking at the statistical properties of the payloads, which is different from the normal traffic. This does not work. For instance, an example of protocol where this will never work is any encrypted protocol. But no intrusion detection system can catch anything in the encrypted portion of protocols, so that's not just my problem, it's a problem of the industry. So what are the results? The results here are that we have a detection rate which ranges by standard tests above 70%. We have a false positive rate of 0.03%. If that seems low, please remember that this is counted in number of packets. So that's not low at all. But in order for you to understand how much better this is than traditional systems, the best rating traditional system working just on the headers can find about 50% of the attacks with a false positive rate that ranges between 0.1 and 1%. So from 1 to 2 order of magnitudes more false positives and less true positives. This is already implemented in a GPL plugin for Snort. Why I'm not releasing it? It's because I'm not satisfied with it. And it's because I don't have the time to support it. So I already know that the day that I put it on my web page for download, I will begin to receive thousands of email support requests, which I cannot handle, which is why you won't find it for download. But if you want it for your own experiments, not that I'm restricting you because it's a GPL, you can then share it, but if you want it for your own experiments, provided that you agree that I will not support you, then just ask me for it. I can share it with you. We have done research in the host-based area. Basically, there's a bunch of ways for doing host-based intrusion detection systems. There's log-based intrusion detection systems, You can look at Daniel Sid's OSSEC for an excellent example of how you can do that. But usually, in the academic area, when you talk about host-based intrusion detection, most of the papers traditionally have worked on the characterization of system calls, because system calls are one of the ways to identify process behavior across different types of processes. All the processes that can violate the security of your system execute system calls, at some point at least. The interesting part here is that usually people look at the sequence of the system calls and at their frequency, but not at the content of the arguments, which is exactly the same problem that we solved for network traffic by applying the two stages process. So we thought, why not to apply the same idea which worked once also to this type of stuff? And what we did was to look at the time series of system calls. We found out that it was very, very different from the time series of packets. And in particular, this is very well modeled by Markov chain models. This is nothing new. I will not spend much time here. If you want, we can talk about it afterwards, because it's been done a number of times. And when I say a number, I mean that if you look for Markov chain anomaly detection system calls, you will find thousands and thousands of papers that talk about this, but always about the sequence. What we did was to bring in, sorry, I don't have time to explain what a Markov chain is. We brought in the idea of looking also at the content of the chain. And how did we do it? It was through an idea which originally came from a professor who has graduated from my university and is now working at UCSB, University of California, Santa Barbara, which besides being a much richer university, is much closer to the sea, and it allows you to do surf after you taught lessons, which is something that you really cannot do in Milan, for fairly obvious reasons. Basically, Giovanni Vigna, with other researchers, developed a system which he called syscall anomaly, which was the first attempt in the world to look at the contents of system calls for anomaly detection. And it developed some very simple models, string length, character distribution, structure of the strings, and inference, in order to deal with anomaly detection. Theoretically, everything was very interesting, but when I actually proved it, and it was not done, as a competitive thing. I was working with Giovanni. When I tried it, what turned out was that each model could be improved. And so, of course, someone, yours truly, improved the models. But besides improving each model, so besides modeling better the various parameters, what I realized was that there was a relationship between the various parameters. So let's give you an example that everyone who is proficient with Unix will probably understand. The most commonly called system call in a Unix program is an open system call. You may have programs that run as much as 95, 98, 100% statistically of their system calls as opens, because open is used for doing basically everything. Trouble is, how do you distinguish between an open being used to read libraries and an open being used to write to a temporary file and an open being used to read /etc/passwd? They're all opens, right? And if you build up a model which comprises all of these things, it will be just too large. It will encompass everything. So it will not detect anomalies. So what we did was to add a step of correlation among the various parameters of a single system call. So we basically created an algorithm which is able to divide your open system calls into various types of open system calls, based on the types of files that they are accessing, based on the permissions that they are using, so that you can actually model the open system call for libraries, the open system call that is used for the particular data file of that particular program, the open system call, how it's used by that program to access the TMP directory. And all of this, I would like to remind you, is done in a supervised manner, which means that I do not rewrite this application or write rules specific to each single program. They are just extracted from a number of runs of the program. So basically, you have to run a program like this in learning mode for a longer time, where it catches all the nuances of the uses of the programs on the machine. You have to create the structure, and then you can use it to detect new anomalies that happen on your machine. This is an example. I'm trying to shorten the presentation because I prefer to take your Q&A and leave the slides to you afterwards to study and to read, than to spend my time commenting the slides and then having to run away from the stage. So basically what happens is that if you take the opens in FD format, which is basically the simplest Unix utility you can find, what you have is a bunch of opens that open libraries. Then there's a couple of opens that open devices. And there's a single open which opens a locale file. If you run our algorithm on this sequence of calls, what happens is that those calls that are in blue right now are collected together because they have the same prefix and they are opened with the same modes. These two are collected together for the same reason. And afterwards, the last call to libraries, which was slightly different from the other ones, is added into that cluster because it's still more similar to the other libraries than to the other things. So what you end up with is that your learning system, instead of having to learn the characteristics of all these bunch of files together, can learn separately the characteristics of the three different types of open that you have. And then you can apply the techniques that have been used and abused in the literature for creating, training, and detecting intrusions over a Markov chain. But instead of building a Markov chain where open is a single node, you have a single state. You have a Markov chain where each type of open is a different state. So if you go from one type of open to another type of open, which is still an open, but is totally different from what you would expect at that point, you will still see an anomaly, which is something that you will not see in the regular anomaly detectors. So basically, what we are left with are a system which detects host-based intrusions, which detects intrusions host-based, a network-based system which detects intrusions, and we are left with the joys of correlation, which you probably already know if you work in this field. As you know, probably, there's a number of products that correlate your alerts and your logs together. They already suck by themselves. But the biggest problem is that most of these products work using classifications of the attacks or types of log events. When you're working with anomaly-based detectors, you don't have types of events. You just have events. So you cannot use the type of event to correlate different things together. And you have to figure out ways, statistical ways, to correlate things that are significant together and to leave out things that are probably false alerts. So basically, one of the things, the first thing that we did, and this works as well in the misuse detection and in the anomaly detection arena, is to use fuzzy clustering concepts instead of crisp time intervals to aggregate events that are close. What happens is that if you have your regular log management system and it has a rule which says, okay, these two events are correlate with each other if they are within 3 seconds of distance. If you have an event which happens 3.1 seconds afterwards, it may still be correlated. You as a human would look at it closely to see if it is correlated or not. But if you have a crisp correlation algorithm, it will just say to you, it's 3.1, it's not 3, so it's not correlated. Using a fuzzy algorithm allows you to give some uncertainty to the result. So you have something which is 0.9 correlated, which means that if one of the two attacks is very, very strongly believed or very, very probable, very, very likely, and you have a 0.9 correlation, you will not discard the two things just because it's 3.1 instead of 3. You will still keep it. And that's one thing. Second part is, how do you actually correlate things that do not have any links together, except for the time when they happened? Colleagues suggested to use Granger causality tests. Granger causality is a concept from econometry, which means that, basically, if some data explains some other data better than some other data explains itself, statistically, then some data is in some way causing some other data. This is a research which was granted the Nobel Prize for Economy, by the way. So, the idea was, use it to try to see if a sequence of alerts, for instance, on a network detector, explain the sequence of alerts on the host detector or not, which is a great idea on paper. On the real world, it's with a small difficulty. The Granger test has a parameter, which is called P, which basically is the time scale over which you want to see if there is a correlation. So for instance, if you are studying the correlation between two different volcanic eruptions, P will probably be set to years because you want to see a long time correlation. If you are studying the correlation between stock market fluctuations and announcements on the press, you will have a time lag which is days or weeks, not years, surely. It depends on the type of problem. Problem is, in the case of anomaly detector alerts, we do not know how close the effect is to the cause. We do not know it precisely enough to scale a Granger test. And we have showed, and one of my colleagues is presenting that right now in Australia, where I will reach him tomorrow. So if you have any questions, make them today, because tomorrow I will not be here anymore. What we showed was that by changing this parameter, basically the test works or doesn't work on different batches of data. If you don't have a way to estimate this parameter, the test is useless. We have proposed also an alternative idea, which is to limit the scope, not to causality in the large sense, but just to see cause and effect in the network sense. So I just want to correlate things that are network and host representation of the very same attack. And we have figured out a way, which is statistically and mathematically a bit too difficult to be placed on a slide at, oh my God, 10 to 5 p.m. But I mean, it's it's a scientific paper, so it will, of course, be open to you for reading if you wanted, if you feel so inclined. Basically, the idea is network systems will see an attack before the host system does, which is basically the only thing we know about how this attack will propagate. Or on the other hand, if it's an outbound attack which comes from one of our machines, vice versa, I will see the activity on the host before I see it on the network. The only thing that I can grasp is that among things that are generated by other things, there will be a significant statistical correlation which is equal to the delay imposed by the network, which is different from the distance that you have between two generic events. So the idea is to use this as a criterion to separate events which may have caused each other and events which have nothing to do with each other. This is still in the works. And anyway, I would like to share with you, and this is basically the end of my talk, a word of caution about results in intrusion detection research. When you see results, you have to think of this Dilbert strip. Dilbert, do you have the benchmark results? Do you want a 10-minute explanation of why they are useless, or a simple, here you go? I'm in sales, here you go. So, basically, benchmarking data is offered to you by the companies with the sole purpose of performing sales. Benchmarking intrusion detection systems is not just difficult. It's the single most difficult task in intrusion detection research. It's a task that scientists do not know how to do properly nowadays. We are still debating it. So it's quite curious that people can say with strong conception that they can, for instance, detect 95.6% of the attacks. How do you calculate that? How did they compute that? How did they compute the speed of their systems? How did they compute the number of lost packets of their systems? I did a whole presentation on why this is very, very difficult and why you shouldn't really believe those figures. And it's available on the Black Hat website. It was Black Hat Federal last year. If you add in the fact that testing correlation is even more difficult, you will understand why. I would advise you to take with caution anyone who says that their correlation system works. On my part, I say that my correlation system seems to work better than the ones that I've tested before it. But I would not claim yet that we have a correlation system that is viable for the market. And I would dare to say that if the scientists in the universities of the world do not yet have a system which is even likely to go to the market, I will buy with a lot of caution commercial systems that pretend to correlate events on big networks with any kind of, credibility. So, these are my conclusions. Which are just a summary of the talk. I will just add some future development hints. We will work on correlation. We are working very, very strongly on that. We are thinking of integrating the host-based system because it works very well, to integrate it as a core force, plugin / rewriting. We are trying to work something out with Core. And we will be performing a lot of real-world evaluation of these algorithms and other algorithms during a European 7th Framework research project, which is codenamed Wombat, which is a small Australian mammal, if you are interested in that, but which stands for Worldwide Observatory of Malicious Behavior and Attack Tools, and which is basically a set of high interaction honeypots that we are going to build and deploy over the next 3 years. If you are interested in that, feel free to ask afterwards. But I basically want to thank you all for attending this talk. That's my webpage. You will find copies of earlier slides, scientific papers, whatever. That's my email. You are more than welcome to redirect your feedback there. And if there are any questions, I will be glad to take them.
Any questions from the floor? The offer of best questions with a free internet security kit still stands.
No one? Well, I will be around, so if you feel inclined to talk with me separately, please do so. Thank you.
Great. Thank you very much, Dr. Stefano Zanero.